Hello everybody, this is Mr. Coker, and I'm going to be trying something this year, putting homework on YouTube, and I will try to explain the homework on the whiteboard and take a little video of the explanations of the homework, and hopefully this will give us more time in class for labs and working on more practice problems. So, just as a starting point here, I want to give you some of my main advice when it comes to handling AP chemistry level questions. So this would be true for AP Chem homework. It would also be true for the AP Chem test. That's the main thing that we're trying to do here in AP Chem is get you ready for that AP Chem test. So the first thing I would say is make sure you read the question. Read it all the way through. Don't just assume that you know what the question is asking. Make sure you read the question all the way through. Number two, read the question. Maybe read the question a second time. Be positive that you understand what the question is asking. Number three, read the question. So read the question, read the question, read the question. This is one of my mantras in AP Chem. The problems and questions that you get in AP Chem are typically longer and more complicated, and you must understand what the question is asking you to do before you get started. Don't just skim the question and jump straight to what you think is the right approach to the answer. The question may be asking for something different than what you think it is. Also, understanding a problem is 90% of solving that problem. So read the question, read the question, read the question. Now, number four, it's important to know the basic algorithms, the basic algebra type problems that you're going to be doing in AP Chemistry. Now, for example, from Chem 1, an ECMS equation, change to moles, mole ratio, solve for the final unit that they ask for in the problem. That's an algorithm. So we have algorithms that we use in AP Chemistry. Sometimes we're using the same ones we learned in Chem 1. Sometimes we're using some new ones. But make sure you understand the algorithms, but make sure, number five, that you understand them well enough that if the problem asks you to veer off from that algorithm, if it asks you to do something a little different than what you're used to doing. For example, think back to the ECMS algorithm. If the question asked you for moles, or if the question gave you moles, it would mean you would skip one of the steps in the algorithm. If it gives you moles, you don't need to change to moles, so you skip that step. If it asks for the answer in moles, you skip the step at the end of the problem where you solve for the unit in terms of the unit requested. You have moles from the third step, you'd already have moles for the answer. So that would be an example of adjusting to the algorithm or adjusting the algorithm to the specific problem that you're doing. So you need to know your algorithms well enough that you even know what to do when the problem doesn't quite fit the algorithm, that you can make those adjustments. Now the two main algorithms we're using on the section 1.A.2 homework, and this is our first book homework of the year, are the first algorithm is to find the empirical formula of a particular compound, starting with the percent composition of the elements in the compound. You need to do percent to mass, mass to moles, divide by smallest, and multiply till whole. So that's a mantra for us. That's a thing that we need to memorize. Percent to mass, mass to moles, divide by smallest, multiply till whole. Repeat it to yourself a few times until you have it memorized. Now the second algorithm is to plug into this particular relationship that the molar mass of an element or the molar mass of a compound, this works for both, can be found by dividing the grams of that element or compound by its by the number of moles of that compound. So if any time in AP Chemistry you can figure out the grams of a chemical and at the same time also know the moles of that chemical, then you have the two numbers that you need to divide to get the molar mass. So without further ado, let's get started with the first problem. Okay, the first problem for the section 1.A.2 homework is number 3.44. Remember, the first thing I told you to do is read the question. So let's read the question together. Peroxyacyl nitrate, PAN, is one of the components of smog. It is a compound of carbon, hydrogen, nitrogen, and oxygen. Determine the percent composition of oxygen and the empirical formula from the following percent composition by mass. It is 19.8% carbon, 2.5% hydrogen, 11.6% nitrogen. And then they're going to want to know what is its molecular formula, given that its molar mass is about 120 grams. So notice by reading the question, we find out that the percent oxygen is not given. So our first step is to find the percent oxygen. Now to do that, we're going to realize that carbon, hydrogen, oxygen, and nitrogen are the only three elements in this compound. So knowing the percent of the first three, we can find the percent of oxygen by simply subtracting from 100, 19.8, 2.5, and 11.6. And we get 66.1% oxygen. Now at this point we are going to pick up on the percent to mass, mass to moles, divide by smallest, and multiply till whole approach. Okay, I've done the first part of the algorithm here. Notice that the percent signs have been changed to grams. So I converted from percent to grams simply by making an assumption that I have 100 grams of the chemical. You can have any amount of any chemical, so assume you have 100 grams of the chemical, and then you automatically know, because percents of 100 are the same number, that you have, in our case, 19.8 grams of carbon, 2.5 grams of hydrogen, 11.6 grams of nitrogen, and 66.1 grams of oxygen. Then, using a technique that we learned in Chem 1 of changing grams to moles, in other words, using conversion factor label method, I've converted each one to the proper number of moles, 1.65 moles of carbon, 2.48 moles of hydrogen, 0.828 moles of nitrogen, and 4.13 moles of oxygen. Now I'm ready for the next step, which is going to be dividing by the smallest and then multiplying till whole. So I'm going to do those two steps next. Okay, after converting to moles, I have now gone through the next step of the algorithm, which is divide by smallest. Now our moles, the smallest number of moles was the nitrogen, 0.828. So I divided each one by 0.828. You divide each one by the smallest. That keeps everything in proportion in the proper ratio, but converts your smallest number of moles to 1. So that's going to mean I have 1 nitrogen. Now, when I do the math and round it off, 1.99 for carbon becomes 2. Hydrogen comes out right at 3, and oxygen comes out right around 5. So that means my empirical formula is C2H3NO5. Okay, so I'm ready to wrap up the problem now. I found my empirical formula to be C2H3NO5. I add up the molar mass of that chemical formula, 2 times 12.01 for carbon, 3 times 1.01 for hydrogen, and 14.01 for nitrogen, 5 times 16 for oxygen. I get 121.06 grams per mole. When I read the question, it told me that my molar mass was 120, and so 120 and 121.6 are about the same thing, and so that tells me that my molecular formula, not just my empirical formula, but also my molecular formula, is C2H3NO5. NO5. If you check the answer in the back of the book, you'll see that that is the correct answer. So we've gotten the first problem done. Okay, our next question is 3.54. This is very similar to 3.44. When we read the question, it says monosodium glutamate, or MSG, a food flavor enhancer, has been blamed for Chinese restaurant syndrome, the symptoms of which are headaches and chest pains. MSG has the following composition by mass: 35.51% carbon, 4.77% hydrogen, 37.85% oxygen, 8.29% nitrogen, and 13.60% sodium. So in this case, they've given us all the percents. We don't have to subtract from 100 to get a missing percent. What is its molecular formula if its molar mass is about 169? So remember our mantra: percent to mass, mass to moles, divide by smallest, multiply till whole, and that's going to get us the empirical or simplest formula, and then we'll see how that simplest formula compares to the molecular formula by using the molar mass. Now, because the problem is so similar to 3.44, I've gone ahead and worked out the rest of the problem. I've changed percent to mass, so in other words, I dropped the percent sign and made it grams. I've changed to moles by dividing by each element's molar mass on the periodic table. Notice in AP Chem we go 2 places after the decimal. Chem 1 only went 1 place after the decimal. And that gives me the moles of carbon, hydrogen, oxygen, and nitrogen. Then I do the step divide by smallest, which is dividing by 0.5916, and I get the ratio of 5 to 8 to 4 to 1 to 1. Now these are all whole numbers, so I can skip the last step, multiply till whole, because I already have whole numbers. Notice a few of them I rounded a little bit, but they were practically right on the whole number. So my empirical formula is going to be C5H8O4, 1 nitrogen and 1 sodium, NNA. So when I add up the mass of that empirical formula, I get 169.13. Now remember, in the problem it told us the molar mass of the chemical was 169, and so since these two numbers match, then I know that my empirical formula, or my simplest ratio, is in fact also the molecular formula. That the molecules formula and the empirical formula are in fact the same. So that's the second problem. 3.98 comes from page 111. It comes from a set of problems in the back of chapter 3 that are called additional problems. I just want to give you a heads up that when you see these additional problems, they're always a level of difficulty harder than the basic problems in the other sections. So that's good. We need to see these hard questions before we get to a hard question on the AP Chem test. In fact, we'd rather prepare with harder questions than the AP Chem test is going to give us, if possible, in order to prepare our best to be able to ace the AP Chem test and get that 5 on the AP Chem test. So read the question, read the question, read the question. A sample of a compound of chlorine and oxygen, I'm calling it up here ClXOY, because I don't know its chemical formula, reacts with an excess of hydrogen, H2, to give 0.233 grams of HCl and 0.403 grams of water. And we are supposed to determine the empirical formula. Now notice I've sort of outlined the chemical reaction that's occurring here. ClXOY plus hydrogen is making HCl and water. But I'm also recognizing that the number of chlorine atoms in this formula will actually be the number of HCl's formed, and the number of oxygen atoms in the formula will be the number of water molecules formed. And that's true because there's only 1 oxygen in water and there's only 1 chlorine in HCl. So that should be 1-to-1 correspondence between the number of chlorines on the left and the number of chlorines on the right, and likewise with the water. So what I'm going to do here is I'm going to skip the steps of doing percent to mass and mass to moles, and I'm actually going to convert grams of HCl and grams of water into moles of chlorine and moles of oxygen. So let me show you how I do that. Okay, so I've divided by the smallest, 0.0639, and I got 1 for the chlorine and 3.5, 1 for the chlorine and 3.5 for the oxygen. So this is our first case of where we're going to need to multiply till whole. 3.5 is not a whole number, but it can easily be made into a whole number by multiplying by the whole number 2, because 3.5 times 2 is going to give us 7, which is a whole number. Now notice if I multiply 3.5 by 2, I also need to multiply 1 by 2, and so I'm going to get a 2 to 7 ratio. So Cl2O7 is my empirical formula. Cl2O7. So I've done a little algebra here, and I've converted the grams of HCl to moles of HCl, 0.00639 moles of HCl. I found the 36.46 to be the molar mass when I added H plus Cl off the periodic table. 0.403 grams of water, add it up on the periodic table, 18.02. I get 0.0234 moles of water. Now I'm going to do a little trick that can really get you a long way in AP Chemistry. We've done in Chem 1 where we've taken the ratio of moles in a chemical reaction and used that to convert from one thing to another. Well, let me show you that actually you can also do it based on the subscripts in a chemical formula, not just a chemical reaction, but a single formula has ratios in it. For example, HCl shows me a ratio of 1 to 1 for H and Cl. So noticing that 0.00639 moles of HCl will need to also have 0.0069 moles of chlorine atoms. It's a 1 chlorine to 1 HCl ratio in the chemical formula. I get my moles of HCl. Likewise with water. Water contains 1 oxygen atom. So that's a 1 oxygen for every 1 water. These are chemically equivalent. 1 oxygen is chemically equivalent to 1 water when you think about the chemical formula of water having 1 oxygen in it. So that gives me 0.0234 moles of water. Now I can go back to my algorithm because I've done something that gets me moles. I can now pick up there with my algorithm and do divide by smallest, multiply till whole. Okay, question 3.102. The aluminum sulfate hydrate, Al2SO4 taken 3 times dot XH2O. In other words, there's water packed into the crystal, and into the ionic crystal. There's a certain number of water molecules for every mole of the compound. And it tells us that it contains 8.20% aluminum by mass. We are supposed to calculate X. In other words, the number of water molecules associated with the aluminum sulfate formula unit, Al2SO4 3 times. So we want to find X. X should be a whole number in these problems. And so we are going to find it by assuming that we have 100 grams of the chemical so that 8.20% is 8.20 grams of aluminum. Okay, I've done quite a bit of algebra here. I've taken the 8.20 grams of aluminum and divided by its atomic weight or molar mass and changed it to moles, 0.304. I then recognize from the chemical formula Al2SO4 taken 3 times dot XH2O that for every mole of the entire compound, I need 2 moles of aluminum. That becomes my mole ratio that I use to convert from moles of aluminum to moles of the entire compound. Then, using that trick that I showed you at the very beginning of this video, I divide grams by moles. Now remember, I assumed I had 100 grams. So I divide grams by moles, I get the molar mass, and the molar mass is 657.89. Now let me show you how I'm going to use that to find how many waters are in this formula. I have that the molar mass is 657.89. Now 657.89 should be the sum of all of the atomic masses multiplied by their coefficients. So 2 aluminums, 3 sulfurs, 12 oxygens, and then X waters means that I can set up an equation and solve for X. So 657.89 is 344.14 plus 18.02X. 313.75 divided by 18.02 is X, and I got 17.4. Now the back of the book says 18. So that must mean that the book, when they worked the problem out, they did a little different job on the rounding, and their answer came out and rounded up to 18. X should be a whole number. If I were writing the solution to this, I would double check my work, but I believe I would say 17, not 18. But in this case, it's pretty close. Let's take a look at 3.106. A certain metal oxide has a formula MO, where M denotes a metal. 39.46 grams sample of the compound is strongly heated in an atmosphere of hydrogen to remove oxygen as water molecules. At the end, 31.70 grams of the metal is left over. If O has an atomic mass of 16.00 AMUs, calculate the atomic mass of M and identify the element. Now in this case, we have 39.46 grams of metal oxide. We remove the water, so we'll say minus X here for the oxygen that's removed in the form of water, and it leaves us with 31.70 grams of metal. So 39.46 minus 31.70 tells me that the 39.46 grams of metal oxide contained 7.76 grams of oxygen. Okay, so I took the 7.76 grams of oxygen and I converted it to moles. Then recognizing from the original formula MO that the moles of M and the moles of O are equal from the chemical formula, I got that it was 0.485 moles of M. Now I'm going to use that trick of dividing grams by moles. 31.7 grams of metal are in the compound. That consists of 0.485 moles of M, and so 65.36 grams per mole is the molar mass of metal M. Put a box around my answer and I'm done, but just because it's kind of neat, look it up on the periodic table. Zinc is our metal. And here's our last problem, 3.112. It's based on a chemical formula XCl3. Analysis of a metal chloride, XCl3, shows that it contains 67.2% chlorine by mass. Calculate the molar mass of X and identify the element. So in this case, we have 67.2% chlorine, which means we have 32.8% X. And I'm going to assume 100 grams, which will mean I have 67.2 grams of chlorine. When I convert that to moles, I get 1.90 moles of chlorine. Now, recognizing from the chemical formula that XCl3 has 1 X for every 3 Cl's, that means I have 0.633 moles of X. Now, using my relationship that molar mass equals grams over moles, I take the 32.8% X and I say, well, that would be 32.8 grams because I'm assuming 100 grams. And 32.8 grams divided by 0.633 moles is 51.82 grams per mole. So 51.82, when I look it up on the periodic table, is chromium. Chromium is actually 51.9961. But that's the closest one, so I say my answer is chromium, and the back of the book backs me up. Thanks for working your way through these problems with me. Hopefully these explanations were helpful.